out with the SN1 reaction is what favors the SN1 reaction, or sort of how do you know when you're most likely to get an SN1 reaction over these other reactions that are present. So one of the biggest ways is the substrate. So notice here that I intentionally put a tertiary substrate. I also put a weak nucleophile / base. And these both are going to encourage SN1 conditions. And specifically, the more substituted the substrate, the more likely it is to be SN1 or E1. And that's because what you get in this reaction is that carbocation intermediate. So we need something that's going to make a more stable carbocation intermediate. Okay, so what favors SN1? Okay, so the rate of SN1 will be fastest with a tertiary substrate or if we have a substrate that is allylic or benzylic. Because the tertiary substrate will stabilize the carbocation by induction. Because these carbon groups these alkyl groups are electron donating groups. EDG. The allylic or benzylic will stabilize the carbocation by resonance. Okay. Also, secondary will work. So second fastest after tertiary, so to speak, is second fastest is secondary. So you can get SN1 with secondary, typically if we have a weaker nucleophile. Slowest would be methyl or primary. And I would say that it would be very rare with a methyl, probably almost, and I won't say, never, but very unlikely. And with the methyl, I would say, primary, I would say very unlikely, unless it's allylic or benzylic. Or maybe if it could rearrange to become allylic or benzylic. So when I'm looking at a reaction and trying to decide which mechanism is the most likely, usually the very first thing I look at is the substrate. And if I'm looking at tertiary or secondary or anything that might be allylic or benzylic, then I'm keeping SN1 and frankly E1 in mind at this point because they're going to have those carbocation intermediates and those things are going to stabilize carbocation intermediates. The next thing I want to look at, so here substrate again, tertiary or secondary, comma, allylic or benzylic. Second, I'm going to consider the nucleophile / base, the other reagent. So for SN1, weak nucleophiles and bases are ones that are the most likely, and you guys have your lists of those already. The next thing to consider is the temperature. So generally, substitution reactions, both SN1 and SN2, are going to be favored by lower to moderate temperatures. And that's going to be because of the entropy factor when comparing substitution to elimination. So when we do a substitution reaction, we have a substrate, we have a nucleophile, and we end up with a product and a leaving group. So here, our entropy, at least in terms of the number of molecules, we can't know for every single reaction exactly what the entropy is going to be based on, the products and the reactants versus the reactants and all of that. But just looking at the net number of molecules, we're not going to have a change in entropy because of that. But if we're looking at elimination, then we have the substrate and we have the base. And then the products will be the alkene product or the product with the new double bond. We'll have the leaving group, and then we'll have the conjugate acid of the base. So here we've made 3 new species from 2. So this is going to give us a positive delta S, and we know that delta G equals delta H minus T delta S. And because of this negative sign here, having a positive delta S, if we have higher temperature, that's going to cause this factor to become more likely to be large enough to overcome any delta H, which might be positive or negative, but it's going to make the reaction more spontaneous. So for elimination, high temperature is favorable. So mainly because of that, for substitution, low to moderate temperatures are favorable. When I say high temperature, I'm usually meaning something like 100 degrees Celsius or higher, and or reflux conditions. So some of our solvents maybe don't boil in as high as water, right? Maybe they boil it like in the 70s, but still reflux would work. When I'm saying low to moderate temperatures, sometimes it could be something in the negative something or other degree range, depending upon the reaction. And then I would say up to room temperature, and above that, maybe to up to like 40 degrees would be reasonable temperatures for substitution to be favorable. Now, every reaction is going to be different. Every reaction you would want to, test and optimize. But that's kind of generally what we're going to see with these different temperatures. So what favors SN1? Tertiary, maybe secondary, allylic or benzylic, a weak nucleophile or base. We do need a good leaving group, but we kind of need that with everything. So I don't see that as being as big of a factor with things. Solvent can also play an effect. However, a lot of times we'll use solvents for substitution reactions that we would, claim to be bad solvents for substitution. So, it's something you can use, again, to optimize things, but I wouldn't use solvent to rule out the mechanism that might be occurring. And then temperature, we want those low to moderate temperatures. And if you have all of these things, then most likely you have an SN1 mechanism on your hands, and that's the reaction you're going to want to draw.